I will talk about the presentation titled as the 7 security features that make up LINE blockchain. I am serving as a software engineer at the LINE blockchain team. Nice to meet you. This is what I cover first. I'd like to start with what is LINE blockchain and including the structure, and also next the blockchain vulnerability, including Bitcoin and others, general blockchains. What are the possible security vulnerabilities? Next, I'd like to talk about the 7 security features versus the blockchain, and especially the LINE blockchain as incorporated security features. And also 7, after the 7 items, I'd like to talk about the more secure idea with my summary. So this is the scope of the presentation. On the service side, there will be an issue of the transaction, that is the transaction record by using cryptography technology on a multiple machines in a distributed manner. LINE blockchain mainnet will cover the processing the record area. As indicated here, LINE blockchain mainnet, consensus on P2P network, the main elements P2P network, there is a transaction from a single machine, and over the other state machines, there will be a propagation. This is what we call gossiping. So the consensus in the all state machines, the generated transactions on all the state machines, there will be a propagation to all the state machines, and transaction, the generation state should be the same as the state in all the state machines. Next, let's look at what's inside. In P2P, as indicated here, there will be a P2P connection, and there will be no distinguishment of the client and the server. And the P2P will be communicating with the nodes and input data. There will be determined by a majority if they are correct or not. So multiple machines will be communicating with each other. So for the all same data set, regardless of the sequence of the input, there will be a same the product to be generated in the blockchain network. In all the computer network, database will be replicated, and the same state will be maintained amongst multiple computers. So generally speaking, there will be intrinsic vulnerabilities for the blockchain consensus cryptography and P2P network. For each area, there will be a specific attack, long-range attack, selfish mining attack. Attacking the block-related the vulnerability, there will be a unlawful length of the change, so that there is a make-believe that it is true. And side channel attack, there will be observation from outside of the state, so that to try to acquire the internal information from there. ECDSA vulnerability is that in ECDSA, there will be a generation of the two signatures by elliptic curve. That's a feature, but they are attacking that it as a vulnerability. And many Bitcoin were stolen from P2P network, and the side coin is attack. The node will be surrounded by rogue devices, so there will be unlawful transaction from there. In the earlier the page, I picked up several blockchain-related vulnerabilities. This time, there are security features. I'd like to highlight 7 security features. Before going to the first security features, there is a difference between LINE blockchain from general blockchain. And when there is a consensus algorithm, which is there is a approval of the block, I would highlight general consensus and highlighting the difference of the LINE blockchain consensus. There is a transaction generated by user. How it will be approved by a block? Let's take a look at the flow. User will send out a transaction, and it will be incorporated in the node network, and the bulk of the transaction will be stored in the block, and the block will be added in the chain, then transaction will be finalized. So if there is a certain remittance of a transaction, it will be stored in the block and it will be approved by a unit of block. Then for the first time, it will be encoded in the chain and the transaction will be finalized. Then next, I'd like to touch upon the proposal from the down to the approval. And there is addition of the block to the chain. There are several types of the consensus algorithm. The proof of work and proof of state, I'd like to highlight it. And there is a difference from the blind blockchain. And first, this is a proof of work. This is a consensus state. And block from A to E, there all the members will make a proposal, and the block with a quick approval by a power will be voted as a yes. However, in this consensus, all the members are proposing for a block, so there is a likelihood that the multiple block will be approved, and there is the node amongst the chain, and we utilize a certain length of the block, and there will be rollback possibility from this stage, and this is the probability finality. Next, proof of stake is the consensus, another type of the consensus. Each node, based on the token held volume, has a voting power, and the block will be approved based on the voting rights. So this is a benefit because no power will be utilized. And if there is aggregation of the more than the half of the vote, it will be approved. So there will be probability finality characteristic incorporate. Next is the line blockchain mainnet. The one leader will make a proposal, and this is a leader selection type block chain selection. If there is a proposal from one leader, there is just one proposal. Unlike the other two, there will be an immediate finality to be enabled. So the leader, the leader will be selected. There is a round robin state amongst the multiple ones. There is an alternate selection of the leaders, but sometimes you can tell who is the next leader. Then this is vulnerable for possible attack. I may have a long winding, but there is a security risks, which I would like to cover from now on 7 security features. First one is about in the selection of the leaders, there will be a selection, the related process, random selection proposal. In the line blockchain mainnet, in the selection of the leaders, there will be a random, the leader will be randomly selected based on the stake volume, and there is a verification approach to verify the selection of the leader, and the identify the theft by the leader will be defended. And for the block proposal among the voters, the requirement says that should be one leader to be selected. But in this there are more vulnerabilities and risks in the line robin set, and there is a run through the process and the waiting and the proof the system will be utilized so that the skill and avoidance of the risks, so that there will be only one leader to be approved in the process. The participants of the chain have the volume of the stake, and it normalized to 0 or 1. And the VRF output is utilized to generate a random number. And when the random number is normalized, then the participants falling into the category will be selected. And the random number and the necessary proof will be prepared. By this process, the proposer of the block will be randomly selected. At the same time, they can prove that they are selected. Could you take a look at the more detailed information?
2つ目のセキュリティ対策は2段階投票とロックメカニズムです。チェーンをフォークさ
Next, two-stage voting and locking mechanism. Next, by two-stage voting, because of there's a likelihood of forming a fork, so I'd like to explain about the countermeasure. In order not to have a multi-node to be voted at the same time, instead asynchronous voting, there's a problem of having multiple votes be approved. are making two-stage voting, and locking mechanisms introduced to solve the availability of two and more different types of blocking being approved. First here is called pre-vote, and the second vote is called pre-commit. And the voter numbers needs to be over 2/3. And the first pre-vote plus 2/3, then one can proceed to the second vote. Then once one gets the over 2/3 and the pre-commit, then moves on to the next stage. On the first to the second stage, within a certain given time, once pre-commit is gathers 2/3, the same height of the different block gets proposed. And top votes being 2/3 being enough, I will explain in the later on. In the second voting, the next block you cannot vote anymore. One can agree to only one block. And why it is essential to have a two-stage voting, I will explain more in detail. The problem with a single stage voting, I'll give some examples. Let's say when the voting for a block nodes goes, and consider a situation where nodes A, B, C, D votes for a block. Nil means a rejection. And suppose A votes to reject and the B, C, D vote to approve. Then A, B, C, D blocks. Then they share the voting message as a gossip. And let's say when the D send the voting message late, D approved, but because A, B, C, because of the transmission issues, they don't have the information. So A, B, C confirms their own voting confirmation, except D. A, B, C has 2 votes, and C gets 3. So that's how we get 2/3. So as explained, A, B, C, D now have a different number of votes. As a result, D is the only one who commits to block. ABC couldn't commit to the block, so then another block X. In the first stage voting, block X and block X dash are on the same height and gets added to the vote, and so there's a fork issue. In order to avoid forming a fork, we created a two-stage voting, and lock and unlock mechanism was introduced. Lock rule is so that the one is restricted to making a vote on one. And in the previous rounds, block can be cancelled. That means when the round proceeds, the other votes plus 2. Once that's confirmed, then you can make another vote. And let me give some examples. A, B, C, D. Let's say they are the voter node. Then one's doing the pre-commit vote, and around R, B, A blocks. Then lock rules is applied. A, C, D, deny. And no locked. So the round proceeds to one stage. Round R plus 1 case, B is locked, so they can only deny. One can only deny. A, B, C, D block X pre-commit. Now the unlock rule is applied. Block X pre-commit is B1. Block A, C, D 3 votes. In unlock rule, in the previous rounds, 2/3. Pre-commit was made, and X lock is cancelled. Now one can vote to Y. And then Y now collected the 2/3 of the votes. So once the pre-commit is made in the rest, the chain can be connected. Therefore, block X, blocks Y each votes can be controlled. So it is to prevent 2 votes being approved. So far, plus 2/3, we have mentioned about how the votes can be conducted. Toward the end, I mentioned that the top votes being 2/3 being enough. I would like to explain. In the P2P connection nodes, malicious node, let's say, is there. That's called the Byzantine node. And it is a malicious node. And once the message okayed and sends as NG, no good. Even with such nodes present, if the 2/3 gets an okay message, we're calling as a Byzantine BFT, Byzantine fault tolerance. And line blockchain main consensus, BFT, the security is delivered from BFT. If it's over 2/3 through gossip, no changes can be made maliciously. So the safety by getting a 2/3 of the votes is guaranteed. And the third security measure is a key management to block the vote, for block vote. The block vote is accompanied by a signature to prevent tampering, and the private key placed in our terminal is used to create a signature. And it's a countermeasure against a side channel attack, including cold boot attack, where the key is physically stolen. And the signature key that's attached to the block ballot must always be online because it requires a real-time processing. So storing the keys in the JSON file on the terminal and loading them into the memory is a security vulnerability issue. So to have as a countermeasure, using Intel SGX to manage keys in secure memory space prevents a ballot forgery. And for example, let's say there is the attempt to steal the private key, and the file, it's inside the memory. Because of the cold boot attack, the way it is not safe. It's possible to approve with a line block the secret key for approval. We use Intel SGX to save it in a safe area to prevent unauthorized signature generations. If you could please refer to secure key management system using N2SGS technology. We've been talking about the blocks, and the fourth security measure is I'll talk about the effectiveness of a transaction. Regarding the transaction approved by blocks, and that's how a transaction gets confirmed. So how can we confirm its secureness? In order to secure many transactions on blockchain, we need a mechanism that can prove that and verify transaction is an efficient mechanism. But it is not efficient to confirm transaction one by one. We can have an efficient way to do the approval. I would like to explain with using example. One, I would like to explain about the flow of transaction. Let's say transaction sent from Alice to Bob. The recipient Bob must be able to verify that the transaction in fact sent from Alice. And to do so, the block contains a proof called Mariko proof. And Bob uses that to approve the transaction. And I would like to explain more on the next page how we use a Mariko proof.
Transaction for the efficiency the operation and will be the data structure. IAVR macro tree utilizes that the system that actually the one individual transaction indexed the form storage will be done from Alice to Bob. Suppose that there are three transactions. The B equal the A equal 1, B equal 2, C equal 3 transactions will be stored. The receiver needs to verify if this is a correct transaction from Alice or not. So Bob will utilize its ABC indexes and they acquire the hash from the ones other than ABC, and we calculate the root value and the proof in the root, and also there is a comparison with the recalculated the hash value. Then if that they are the same, the verification will be done. So Line blockchain mainnet utilizes IAVL macro tree. So instead for the individual transaction is performed individually, the verification done by the Bitcoin macro tree, but the IAVL macro tree can finish it with just one go, and it's more efficient. So next, the fifth security measure is ECDSA curve order. So actually, ECDSA malleability, the ECDSA is the main form of the usage of the block phone. However, it's possible to forge a transaction. Then unlawful transaction will be just passing through. Back in 2014, the Mt. Gox, which is the global, the largest exchange, as much as 740,000 Bitcoin was stolen. Through this kind of attack, when there is a signature for certain transaction, another person's the signature can be forged to verify that transaction is valid. Then there will be a generation with 2 or more transactions utilizing the vulnerability. So in the case of generation of the signature, there should be a proof. So ECDSA, the elliptic curve SCCP256K1 has specific features which could be leading to the 2 valid signatures as a solution out of the curve generation. There should be an approach that to make sure that only one will be valid. Transaction generated from Alice will be converted in hash value, and there will be documentation generated based on the elliptic curve and using one private key. And the SIG are generated for signature, even though without the usage key there will be issue because it's possible to generate another one. So there is actually module the calculation to be utilized by using a prime number. This is the axis based asymmetry. There will be a generation with 2 signatures. So there should be a split. The upper half from the lower half. The lower half should be valid and the upper half will be invalid. By setting that rule, we overcome this kind of issue. As you can see, in the case of primary number 11, in this case, there would be 4. It's based on the module operation will become 7. Upper half is invalid, 7 will be found to be invalid. So in this manner, there will be a check of the validity so that we can eliminate this issue of the generation of the valid signature. There will be 2 valid signatures to be generated. Next, I'd like to talk about the feature to detect malicious node and report. And the detection of the rogue node and how to report it. There is Eclipse attack. The node will be surrounded by rogue attacks, and there will be a gossip to be compromised. How we will be make a countermeasure against it. So multiple nodes exist. They are gossiping, and there is communication data by them. But communication should be correctly done. If it is hindered, there will be a damage to the system. There should be a detection system to find the rogue nodes. All the data of the block will be needed, but it will be leading to a higher cost because it utilizes the usage of the storage. There should be another system so that right nodes will having a transaction list to detect and report such nodes. Let's take a look at the system as indicated here. Write nodes observes node A, and to make sure that they are correct. If there is a logfulness detected, there will be a generation of the evidence, and there will be a broadcast to nodes B and C. Let's take a look at the next page and how exactly they are verifying. So the target node is a primary node, and witness node is evidence reported nodes. Write node from primary node acquires the log header, block header, acquired block header from witness node to there will be a comparison of the information with the witness node. So as indicated here, write nodes, the height 11 and 12 for the primary node, and the witness node, the height 11 dash and 12 dash, they are retrieved. And they compare between the two, and they pinpoint that there is a discrepancy. And the primary node and the witness mode on one-on-one, if there is a discrepancy, you cannot tell which is a malicious node. Then, as a countermeasure, you will acquire the further header from multiple nodes. By acquiring the header information from multiple nodes, you can tell if that particular node is really log or not. If it is a log, then evidence will be broadcast to all the nodes. Only the discrepancy on the nodes will be detected, and the results will be sent out to witness node. This way you can save the cost of the detection. The 7 is the last security measure. In the last section, and there was I reported that how the log node will be reported. In this section, by using retrieved data, we will establish trust for the node so that better quality peer will be selected for the connection. And on a peer-to-peer gossiping will be done for the data. In that case, there could be a breakage of the data, and there are some peers making a try to malicious revision. And this will be, if this happens, leading to the total damage of the system. So there should be a connection linked to the quality good peer. So you need to quantify the good peer and the data alteration and other the bad events versus good events. They are compared and trustful value, and also you will acquire the trustful values so that they are based on the past and present information. You can make a judgment who are the good ones. And for the nodes gossiping each other, the nodes will have address book, something like a phone book, as indicated here. Node is connected from A to E. In this linkage, address book listed up them, and each node has a trustful value and trust information. As in the other slides, if there is a detection with log the node that is recorded as bad event. If there will be no delayed event, the event will be recorded as good event, and the trust value will be updated based on the event, and there will be a lineup of the trust.
的にゴシップすること
Gossiping to the addresses with the highest trust value prevents performance degradation in communication. Then next, let's look at how confidence values are calculated using events. We are adding all these values, and this is all the latest values that has changed. Good peer, all of a sudden acting as a bad peers. We are calculating trust metric. And when making connection, connect to the one with the highest trust metrics, improves trustworthiness. This, if you would like to know more about how we provide the trust levels, please refer to this link. So I have introduced to you our 7 security measures. So these are the measures that we have in the line blockchains. And when having more transaction, of course, we'll need to do the proofs more often. We can use RSA accumulator, point proof, and those are the new technologies. And also, it's quite a challenging topic in order to anonymity and privacy. That's an important security issue. In the past, unauthorized mining occurred frequently on Monero, and making a challenge to balance transparency and security. But I personally believe that the 30 years ago developed method IEA Schnorrs developed, and now I believe that the issues can overcome technically in future. We will continue our research and development incorporating the latest technology so that the Line blockchain service can be used by many people. Thank you very much. Thank you very much, Ms. Shozawa. Now, we would like to turn the microphone over to the interviewer and have the interviewer ask questions to the presenter, Ms. Shozawa. And the participants are welcome to send us questions to Ms. Shozawa too. Please use the question button at the bottom of your screen. And the interviewer is Mr. Muroga Daiki from Line. Thank you very much, Ms. Shozawa. I am Line blockchain engineering team. My name is Muroga. Consensus measures sending P2P protocols are developing from outside, and making sure that when running the blockchain as a service, there's no issues. So I'm doing things like that, testing things like that. Thank you very much for today. Thank you. So, Muroga-san, if you have any questions to Ms. Shozawa. Yes, I have a few questions that I'd like to ask. So what Ms. Shozawa was saying in the beginning, proof of stake, probability finality, you're proposing is a questionable. Ethereum 2.0 of these days, it has the ultimate finality, isn't it? Absolute finality. Yes. Using more gadget functions, Ethereum 2.0, there's absolute finality. Yes. That's a trend. So attaching finality, I believe, is an ongoing trend. I see. When having more users, finality impacts usability, so I believe it's becoming more and more important. And at the same time, the blockchain that's available in the market, I think most has more probability finality. So the transaction that you send can be lost. Is that really a possibility? Yes. Bitcoin is a good example in the form of unconfirmed transaction. Unconfirmed, those are listed. Unless confirmed, it is possible that your transaction get rolled back. So that means there's no transaction. Transaction was not established. I see. So the transmitting funds, let's say with a blockchain, the transaction is still going. Yes, it can take a long time for the transaction to be completed, or it can, in the worst case, get canceled. I see. In that case, on comparison, Line's blockchain has finality. So in case of monetary transactions, there's no such thing as unconfirmed or cancellation, correct? Yes, because we are realizing immediate finality, so the transaction is confirmed right away.
So in order to such a finality, perhaps it is important that the block will not fork. One of the reasons that no forking, there should be one proposer only. So in selection of the proposer, VRF might be used, and you touched upon it. For VRF, which node? There may be many nodes and validators who will be selected as the only one proposer. In initial stage, the selection of the one, there is no fixed approach. Even it's okay that it's not determined yet, but there's an input value, block height, and round and genesis block information are utilized in the initial stage. As long as the input value is the same, whoever the executing it as an output hash value will be the same as a deterministic theory base. So who will be, regardless of who executes it, the same value will be generated. That's a feature of the VRF. I see. So for each node, will execute VRF, and if they notice that they are the proposer, they will be getting into the proposer status. So first, there will be a generation of the output. Regardless of who does that, you get the same value. This is a hashed value. So hashed value can be dealt with as a random number. We determine who will be the one. And the second rank and onward, the previous hash value will be utilized, and the proposer will execute the operation. I see. I understood.
でそこ
So after the selection of the proposer can also be validated too, right? Yes, when making block, proposer creates a proof with confidence. So me being the proposer gets recorded on block. I see. So once the proposer is chosen and proposes the block, yes, and then the consensus starts, then the way to not create forks, two-stage voting you were talking about. And two-stage voting, having a 2/3 of the votes, the other votes block. So you said it's possible to transfer from the first block to the second one, which attained 2/3 of the votes. So that means that the other blocks gaining the 2/3 of votes, does that mean that that gets committed right then and there? That's what I thought, listening to your explanation. What's the benefit of switching the voting from the first to the second? Well, having the 2/3 of the votes, two times approval, having the 2/3 of the votes twice, then the block gets committed. Yes. But in case the approval was not made, the round change allows the blocks that you voted, if it's not approved, that becomes a blocking, that becomes a lock. So one cannot vote for another block. So 2/3 votes cannot be connected. So the more rounds and rounds, new blocks are proposed. So if you're locked within in the old block, then it's possible that one can never get the 2/3 of the blocks. Then the same height blocks goes on a loop. Then the consensus process does not carry forward. So in order to prevent that, we need that rule of lock and unlock both at the same time. I see.
Thank you very much. So 1/3 or less would be a factor to realize VFT. So the feature, security feature number 6, right node would monitor other primary nodes and their witness nodes involved for hashing, for further looking at. And there are multiple involved because Byzantine is 1/3. Based on that assumption, this witness nodes, number of witness nodes will be determined. The setting up the witness nodes, 1/3 rule will be broken. This is a kind of backup feature when the 1/3 rule is compromised. So as many witness would be utilized to monitor primary nodes. That's the main feature of the detection and reporting. Oh, I see. So you got primary nodes, 1, and witness node, there are 4. Then the Byzantine node would be 1/3. That's not the case. So ideally, we should have as many as possible nodes to watch out for the primary nodes. As many as that might be less accurate. The number of participants, you can specify the number of witness nodes. So calculation speed will be another factor to consider too. So it's up to how you use the system. Okay, thank you very much.
So this may be my last question. Line blockchain, what kind of security challenges that you are facing right now? In the future slide is up. Do you have any challenges that you're facing right now for Line blockchain? Yes, when we have more participants or connecting chain to chain, that's also something that we would like to realize as an option. We think that will be the service that we like to offer in future. So IAVA Markov tree it's a function sets to confirm that the transaction was valid, successfully completed. Multiple transaction being a valid transaction can be confirmed, but we need to generate proofs every single time for confirmation. So that impacts the storage capacity per transaction, every transaction. So we would like to congregate the proofs, which allows us to scale better. It can be a better so-called community system, we believe. So that's something that we are working on right now to improve usability. Thank you very much. So that type of performance enhancement is something very much that I'm interested in working on too. So I hope we get to work together with you on that. Thank you so much for your very clear presentation. That's all from me. Thank you very much.